we are trying to do a translation. We said we come from the visible part. So what is necessary to make color visible? So we need a light source, and to measure it, we need a light source as well. We need some light. Then we have an object, and in measurement, we are using a sample. So either it's direct the object or part of it. And then instead of the observer, we are doing data processing, and then we have a measurement instrument. So this visible part is very subjective, and here we can reach objectivity. So now what are we doing with these three measurement elements? We have the light source, the sample, and the data processing here. And we want to implement that instrumentally. So we have to select an illuminant. We have to measure the reflection of the sample. And then we need to select the standard absorber. And now, what are we doing with all of that? So to really get a unique value for a certain color. So what's happening in a modern spectrophotometer? We have the light source, light falling onto the sample. Then it's refracted by a holographic grid. We have a diode array measuring the whole spectral curve of the light falling onto the holographic grid. And now we have all the data. You see the reflection curve, you see the luminant, and you see the three observer functions. What are we doing with all of that? So I will now explain you shortly the calculation which is taking place in the instrument. Just to give you an idea, of course, it's not easy to grasp all of that at once. Okay, I have selected some illuminant here, for example, T65. And then the measurement is giving me a reflection curve. What's happening now is that a multiplication takes place of two curves. So for example, I take the value for light blue here and the value for light blue here, and these values are multiplied, and I get a value for light blue here. And I'm doing that for every nanometer, and I get another curve that's now called the visual stimulus. Then again, one is multiplying these visual stimulus with the CIE observer functions. So it's three multiplications. I multiply this curve with that curve and get another curve. I multiply this curve with the green curve and get another curve. And I multiply the visual stimulus with the blue curve and get that curve. Yeah, and you see it's very low here, though the observer function is lowered here, for example. And then in the end, one is not only, one does have this curve, but a curve doesn't give a single value. And what is done now is an integration. That means the area under the curve is calculated together. So it's you're calculating how much area is it here. It's 49 for under the red curve. It's 37, you could say, squares or units, yeah, under the green curve, and only 8.6 is the area under the blue curve here. And now we have three values, capital X, Y, and Z, and these are characterizing our object here. So to see it in the instrument again, I have the light source. Just a moment. So I have the light source, the sample, holographic grid, diode array, and all the data. Light is falling onto the sample, the holographic grid, the spectral curve is measured, and then I have a data processing inside the machine, and I get these three color values, X, Y, and Z. So that's the data output for measuring that yellow sample. Okay, so now we have, we aimed our goal here. So we have unique values. So if you're measuring that yellow, you would only get these X, Y, and Z values. And if you have these values, they wouldn't correspond to any other color. So they are unique to this color. And that is very important. So one didn't have that before that kind of measurement was invented. It's uniquely described. So we have, we meet our goal here.